SwayamPrabha. Digital India. Educated India.
Today we will continue our discussion on the flow mode analysis using the Herschel-Berkeley fluid model. So, we saw that our region has three sub regions, I would say 1, 2 and 3, where the velocity profile is different, and the shear strain variation we saw them to be linear, and we found out the velocity distribution over each of these 1, 2 and 3 region. And then we are finding out the effective damping, and for finding out the effective damping we found out the total flow rate Q, and then we have to equate this total flow rate Q with the total flow rate obtained from a equivalent constant velocity um. So, assume equivalent constant velocity um. So, it is constant over the cross section. So, it is constant means constant over the cross section. And then if it is so, then our total flow due to this is um multiplied by b into d, and as we know b is the dimension over the other direction. So, this is our x, this is our y. So, width of the plate we can consider that to be b. So, b is our dimension over the z direction, which is perpendicular to x y. So, we have um into bd. Then we can equate this with q. So, if we equate q is equal to um bd, and that helps me evaluating um. So, um becomes n multiplied by delta p by k l to the power 1 by n, and then we have 1 minus delta bar divided by q n plus 1 by n, and we have n multiplied by 1 plus delta bar plus 1 divided by 2 n plus 1 by n plus 1 multiplied by d into n plus 1 by n. So, here delta bar is our del by d, which we defined before also. So, everything so this delta has been non-dimensionalized with respect to d, and the expression is written. So, we got that just by equating q with um bd. Now, here we can see that our um is a function of delta p to the power 1 by n. So, in such a case, if I want to find out the equivalent damping, then it would come out as a function of delta p. So, we can do that, or we may want to express our equivalent damping as a function of um also. So, if you want to do the other way, which means if you want to find out our equivalent viscous equivalent damping in terms of then better we express delta p in terms of If we do that, then it becomes delta p equal to k L d to the power n to the power n divided by n to the power n multiplied by 2 by d minus delta n plus 1 and then within a bracket we have these quantities 2n plus 1 multiplied by n plus 1 divided by n into d plus delta plus d to the power n, and again we can take out d and now write this entire expression in terms of delta bar as well, like we did before. So, this is just, this relation is just an inversion of this relation, where I am expressing delta p in terms of u m. Now, our finding out the equivalent damping is coefficient is simple. We write a force corresponding to this delta p, and the force is delta p multiplied by B d. So, force F, which we can say the force responsible for causing the flow, that is delta p multiplied by B d. So, damping coefficient now this damping coefficient is in the active mode when the fluid is active. So, we can call it active damping coefficient, and that is equal to F by u m. So, F by u m finally comes out to be u m to the power n minus 1 multiplied by k b l d to the power n plus 1 divided by n to the power n multiplied by 2 by d minus delta to the power n plus 1 multiplied by 2n plus 1 multiplied by n plus 1 by n into d plus delta by d, and we have to the power n. And then this quantity can be written in a non-dimensional form as u m to the power n minus 1 multiplied by k b l divided by n to the power 1 n to the power n d to the power n multiplied by 2 by 1 minus delta bar, where delta bar is delta by d to the power n plus 1, and then we have the same thing within the bracket 2n plus 1 n plus 1 divided by n into 1 plus delta bar plus 1 to the power n. So, this is our active damping coefficients. Now, here we can see that the active damping coefficient, as we expected, it is a function of u m, which was not the case previously when the flow was when we are using the Bingham plastic model, because in that case n was equal to 1, and if I put n equal to 1, then this quantity just becomes 1. So, it becomes the damping coefficient becomes independent of the u m, equivalent flow velocity. So, if I want to compare this with inactive damping coefficient, we should compare for the same u m, and inactive damping coefficient can be found out just by setting delta bar to 0. So, inactive damping coefficient, which means the damping coefficient when there is no electric or magnetic field applied, which means when tau y is 0, and we know that at that time delta bar is equal to 0, because there is no concept of yielding at that time. And if we find out the inactive damping coefficient, which we can do just by setting delta bar is equal to 0 in the expression of active damping coefficient, the inactive damping coefficient becomes u m to the power n minus 1 by k b l divided by n to the power n d to the power n multiplied by 2 to the power n plus 1 multiplied by 2n plus 1 to the power n. So, the ratio of active and inactive damping coefficient can be obtained from here in terms of this non-dimensionalized plug thickness delta bar, and that becomes 1 minus delta bar to the power n plus 1 multiplied by nth power of 1 by 1 plus n delta bar divided by 1 plus n. So, this is the ratio of the active and inactive damping coefficient. Now, here if we set n is equal to 1, we will get all the quantities that we got using the Bingham plastic model. So, it is as advisable that the learners try to plot the flow profile and try to evaluate these expressions for various values of n. So, that will give an idea of how the flow profile changes when we incorporate n more than 1, that means the shear thickening case, or we incorporate n less than 1 in case of in the shear thinning case, and which can be easily done with the help of platforms like MATLAB. Now, this brings us to the end of this flow analysis using the Herschel-Berkeley model. Next, we will do the similar analysis using Bingham biplastic model. So, Bingham biplastic model is a modified version of the Bingham plastic model to incorporate shear thinning or shear thickening behavior, and that can be read, the little bit more details about the model can be read in this paper that is referred here. Now, in Bingham plastic model, we have seen that the variation of shear stress with shear strain is just this. So, this is Bingham plastic model. So, in the entire region, in the entire I would say post yield region, our del tau by del gamma dot is constant. So, there is no shear thickening or shear thinning. What the Bingham biplastic model says is that this post yield region, they divide it into two parts. So, depending on whether it is shear thinning or shear thickening, the graphs would look like this. So, if it is shear thinning, okay, let us do it for shear thickening first. So, if it is shear thickening, the graph looks like this, and again it is same whether we are in the positive side or negative side, just the sign changes. So, we can see that after some value of shear strain rate, the slope of the stress versus shear strain curve increases, which means the viscosity increases. So, it is shear thickening. So, this is shear thickening. And then we have something like this when I have shear thinning effect. In that case, the slope is more before and less after. So, this is shear thinning. We can call this slope as mu 0 and this is mu 1, here this is mu 0, here this is mu 1. So, in this case our mu 1 is greater than mu 0, in this case our mu 1 is less than mu 0, and this is Bingham biplastic model. And when you have mu 1 and mu 0 same, it becomes the Bingham plastic model. And again please understand that the graph here and the graph here are same. So, mu 0 here and the mu 0 and the negative side is same, mu 1 here and the mu 1 here are same. Similarly, tau y, the yield stress is same at the positive and negative side. So, whether the fluid is moving towards the positive direction or negative direction, it does not matter. Now, we have to look at the equations, how to write this entire thing in the form of equation. Now, when we have gamma dot equal to 0, which means the flow velocity gradient is positive, we have tau equal to tau y plus mu 0 gamma dot, given that gamma dot lies between 0 and gamma t dot. Now, gamma t dot is the strain rate at which the slope change occurs. So, that is denoted as gamma t dot. Now, irrespective of the electric or magnetic field that we apply, that means irrespective of the tau y, gamma t dot always remains same. So, if we apply high electric field, this graph just shifts parallelly up. So, the gamma t dot remains same, and the gamma t dot is same at the negative side also. And then we have tau equal to tau I plus mu 0 minus mu 1 multiplied by gamma t dot plus mu 1 gamma t dot when our gamma dot is more than gamma t dot. That means, when we are in this region or in this region. Now, this what we saw just now is based on the fact that gamma dot is more than 0. That means, we are looking at this graph or this graph. Now, we will look at the negative side of the graph. That means, when our gamma dot is less than 0. So, gamma dot is less than 0, and then the equation looks like this: tau is equal to minus tau I plus mu 0 gamma dot is a negative quantity now, and when the magnitude of gamma dot, which is minus gamma dot for this case, is less than gamma t dot, and then tau is equal to minus tau I minus mu 0 minus mu 1 into gamma t dot plus mu 1 into gamma dot, and that is when minus gamma dot is greater than gamma t dot. That means, the magnitude of gamma dot is greater than gamma t dot. So, we will use this relation now for analyzing the flow in the flow mode or valve mode. Now, because the model is biplastic, if we look at the flow region, instead of seeing 3 regions, we would see 5 regions. So, again we have 2 plates which are fixed at their position, and we can take an axis at the mid line now instead of the bottom line x, and this is our y. So, here we have a plug region. So, this is our plug region between these 2 dashed lines, and where our velocity gradient is 0, and then between the end of the plug region and the plate there is a junction where below which we have gamma magnitude of gamma dot less than the gamma t dot, and above which we have the magnitude of gamma dot greater than gamma t dot, and same thing is at the bottom half also. This is symmetric. Now, because of the symmetry, we will do the analysis starting from the mid region. Now, this is our delta, this is our d. Now, we call this distance as y is equal to delta by 2, and then we call this distance from the mid region, mid line to the line where the two posterior region meets, that means where gamma dot is just gamma t dot, and we call that as yt, and then we have from the mid region to the upper plate, from the mid line to the upper plate, that is d by 2. The velocity profile, if we see, it would look something like this. You can show it in a different color maybe. Again, this is constant here and this is symmetric. So, it's like this. Now, this is what we have to analyze. So, here our approach is that at first we write the shear equation, and from there we will find out this y, yt, and then we will start solving for the velocity. Now, while solving for the velocity, we will start from the uppermost region. So, we name the regions like this: region 1, region 2, region 3, 4 and 5. So, we will start from upper region 5. So, we will put the boundary condition at y is equal to d by 2, and then we will put the continuity condition at the junction between region 4 and 5, and that will help us finding out the velocity profile at 4. And if I get the velocity profile at 4, we know that the velocity between the junction of region 3 and 4 is the velocity in the region 3, and that helps us finding out all the velocities. And then from there we can find out, again using the same approach, the equivalent constant velocity, and that can help us finding out the damping coefficient. Now, our governing differential equation is del tau by del y is equal to minus del p by L, same equation, and that gives us tau is equal to minus del p by L into y plus C1. Then we put the boundary conditions. So, here our y is equal to 0 is the mid line, that means the middle of the plug region, and we know that at that region our shear stress is 0. So, we can say that at y equal to 0, tau equal to 0, and from there we get C1 equal to 0, and then at y equal to y1, which means here we have at y equal to y we call that at y equal to y is equal to d by 2, we have tau equal to minus of tau y. It is minus because the velocity gradient is negative after that. So, it is minus of tau y, and that gives me that y equal to tau y multiplied by L by delta p, and from here we can say that delta is equal delta, the thickness of the plug region, is equal to 2 tau y L divided by delta p. Next, we will put the condition that at x equal to y t, at y equal to y t, we know that tau equal to minus tau y minus mu 0 gamma t dot. And that tells me that minus del p by L y t is equal to minus tau minus mu 0 gamma t dot, and by solving this we can find out y t as mu 0. Okay, so it is tau y. So, it is mu 0 gamma t dot L divided by delta p plus tau y L divided by delta p. So, we have now characterized all the regions in terms of their dimensions. Now, we have to look into the flow profile. So, for the flow profile we solve the governing differential equation in terms of the velocity, and as we said before, we will start with region 5. So, in region 5 the shear stresses tau as a function of y is equal to minus of tau y plus mu 0 minus mu 1 into gamma t dot plus mu 1 into del u 5 by del y. So, u 5 means u at region 5, and that gives me, I mean that quantity is equal to minus del p by L into y. So, from here we can write that del u 5 by del y, if we just in this equation if I just write everything in terms of del u 5 by del y, that becomes 1 by mu y of tau y plus mu 0 minus mu 1 into gamma t dot y plus 1 by mu 1 into minus del p by L y square by 2, and then we can integrate this quantity, and that will give us u 5 as a function of y equal to one by mu 1 into tau y plus mu 0 by mu 1 into gamma t dot. Okay, so now from this expression, if I express everything in terms of del u 5 by del y, I get del u 5 by del y equal to 1 by mu 1 multiplied by tau y plus mu 0 minus mu 1 into gamma t dot minus 1 by mu 1 into delta p by L into y, and then we can integrate and now we can integrate the equation, and that will give me u 5 as a function of y as 1 by mu 1 multiplied by tau y plus mu 0 minus mu 1 gamma dot into y minus 1 by mu 1 into delta p y square by 2 L plus a constant C 1. Now, we need to evaluate the constant, and that we can do because we know that at the upper plate, which means at y equal to d by 2, u 5 is 0. So, if we put this boundary condition here, then finally, we can evaluate our C 1, and the final expression that we get is y minus d by 2 divided by mu 1 multiplied by tau y plus mu 0 minus mu 1 gamma t dot plus y plus d by 2 multiplied by minus delta p by 2 L. So, this is our velocity profile in region 5. After that, we will find out the velocity profile in region 4 and region 3, and then from there we will proceed for finding out the equivalent damping coefficient. So, we will do that in the next lecture. Let us end the lecture here. Thank you.